Hello.
Hi, Luís. Hi, everyone.
How are you?
I'm good. How about yourself?
Good.
Hey, Luís. Hey, Paulo.
Hi. Hi, Troy.
Hey, Troy. It's a little late over there.
Yes, it is.
This is a little strange. My name is
Recording
not
in progress.
Okay.
I think maybe we can get started. Good morning, everyone. My name is Shinri, and I'm an associate publisher at Cambridge University Press. Thanks for participating in our joint symposium today, held by the journals High Power Laser Science and Engineering, and also Journal of Plasma Physics. And we thank Chinese Laser Press and Laboratory of Plasma Physics at Shanghai Jiao Tong University for their support on this event. For our today's symposium, we aim to better promote the continuous progress and development of the laser plasma research and related applications, and also to celebrate the 10-year anniversary of high power laser science and engineering as a great milestone of the journal. So next slide, please. So our symposium today will cover 5 academic lectures by experts from Europe, US, and China to talk about their research on laser plasma interactions, and also a panel session where the editors of the 2 journals will be talking about their journals and interact with our audience. And now I'm pleased to welcome Dr. Xiaofeng Wang, the chief editor at Chinese Laser Press, to give us an opening speech.
Okay. Good morning and good evening to everyone. I think you can hear me, okay? Hello, can you see me? Can you hear me?
We can hear you.
Yeah, okay. Good. I'm Xiaofeng Wang from Chinese Laser Press, one of the co-publishers of the journal High Power Laser Science and Engineering. 2023 marks the 10th anniversary of High Power Laser Science and Engineering. As the chief editor of Chinese Laser Press, I'm pleased to welcome you all to this webinar. So far, the journal has published more than 450 excellent articles from 31 countries and has established itself as an important journal in the high-power laser and the related fields. Due to the tireless efforts of the researchers and scholars who have contributed to the advancement of knowledge through their work. I'm very proud to see that the journal has played a significant role in the pursuit of knowledge by publishing high-quality research and fostering global collaboration. Our team has worked diligently to ensure that every article, review, and commentary that we have published meets the highest standards of excellence in research and scholarship, while also being accessible to a wider audience. This event provides researchers in laser plasma field an opportunity to freely exchange their ideas and perspectives. We're honored to have such a prestigious group of scholars and experts in attendance. I would like to take this opportunity to personally thank all of you who have supported our journal over the years. Your contributions as authors, reviewers, and readers have been instrumental in our success. We will always be committed to promote meaningful research. Once again, welcome to this webinar and thank you for your contribution to the advancement of knowledge. We look forward to continue our collaborative efforts to enhance the scholarly community. Thank you. That's all.
Thanks, Dr. Wang. We definitely look forward to more collaborations with high power laser science and engineering and also CLP in near future. So let's now move to the academic lectures. Our first panelist today is Professor Luís Silva from University of Lisbon. Professor Silva is president of the School Council of IST. His research focuses on the in silico exploration of the interaction of intense beams of particle and laser with plasmas, combining theoretical physics with massively parallel numerical simulations in the laboratory and also in astrophysical scenario. Professor Silva is also the fellow of American Physical Society, the European Physical Society, the European Academy of Sciences, and also corresponding member of the Lisbon Academy of Sciences. So welcome, Professor Silva.
Great, thank you so much for the invitation, and it's a pleasure to be here, not only from a Journal of Plasma Physics as a member of the editorial board of Journal of Plasma Physics, but also as an author of papers in both the Journal of Plasma Physics and the journal that we are celebrating here today. So it's a great pleasure to be here and to share with you a little bit some of our research. So I will try to share the screen, which I think you're probably seeing at the moment. And so this is a brief summary of some of the efforts that we've been pursuing in the past let's say 5 to 10 years on exploring plasma kinetics with the ultra-intense laser. So I'm going to take you to some of the research directions that we've been pursuing more recently. So this work is done in collaboration with people in my team at IST, namely, so I'll be showing essentially work done by Pablo Bilbao and Thales Silva, also in close collaboration with Weilong Zhang and Thomas Reismeyer. And also many of the results that I'm going to show have been performed using supercomputer resources in Europe and at IST. That's also I would like to acknowledge here. So what the topics that we've been pursuing can be described as what we call extreme plasma physics, which is essentially plasma physics which is supplemented by additional physical effects. There's a very nice preprint on arXiv by our colleagues Dmitry Uzensky and others that describes this from the astrophysics point of view. But if you look at the physics that is involved in these scenarios, you will recognize that many of these effects are also present in laser plasma interactions. So when we are talking about special relativistic effects, radiation reaction, electron positron pair creation, this is something that we find both in relativistic astrophysics and ultra-intense laser and particle beam. So we've been trying to pursue these two directions and finding connections in these two directions. So where can these interplay be important? I think it's an important way to benchmark numerical models and understand the reduced scales. Since in astrophysics, the physics is inherently multi-scale, so this interplay between lab and astrophysics is important to understand how these scales are connected. In many of these scenarios, the plasma instabilities and plasma dynamics can be modified by QED processes at lowest order. Radiation reaction that I will discuss a little bit more in detail is more important. And if we go to even higher intensities, from either from static fields or from electromagnetic fields, one can even look at avalanches or cascades of electrons and positrons. And so what we've been trying to understand is also how this self-consistent pair plasma is formed and what is the effect of QED on the plasma dynamics, for instance, in the gaps that occur in the polar caps of compact objects like neutron stars. And of course, in all these processes, we have radiation emission, either at very high energies, synchrotron radiation, or at low energies. And at low energies, we know that in many astrophysical processes, we see coherent radiation in the radio or rather the low wavelength radiation. So We want to understand what is the interplay between the nonlinear dynamics of the plasmas driven by ultra high intensity electromagnetic fields and these processes that can occur at much lower frequencies. So what I will try to do today is to take you a little bit through this interplay to look at plasma kinetics and their connection with intense lasers and quantum electrodynamics, and then give you a couple of examples of some of the research, more recent research that we've been pursuing, either in connection with radiation reaction affected by and how this affects the plasma dynamics, and then how can we mimic some of these plasma kinetic processes driven by QED in the laboratory using high-intensity lasers. So we think these are two very interesting frontiers that bridge this gap between plasma physics and laser physics, or make this connection between ultra-high-intensity lasers and relativistic astrophysics, always with this underpinning connection of plasma kinetics. So one of the most exciting avenues for research with intense lasers is this vision of creating electron-positron pairs in the lab. And I always like to show this movie that was first done by Thomas Weissmeyer, because this illustrates the richness of the physics that we are talking about. So this is the most simplest setup that you can imagine. You have two electromagnetic waves, and you just have one single electron here sitting in the center. But these two electromagnetic waves, they have huge intensities. So the intensity here is over 10 to the 24 watts per square centimeter. As expected, when we let the two lasers come together at the center of the simulation window, they start to interact with the electron. The electron starts to quiver with relativistic velocities in the laser field. As it oscillates, it starts to radiate strongly. So lots of photons are emitted. These are the ones in yellow, and the photons themselves are going to interact with the laser field. They are going to generate positrons and electrons. As you can see, just from this simulation, the physics is quite complex. There's this exchange of energy from low energy photons, infrared photons, into high energy gamma photons. And then in turn, these photons interact with the laser field again, and they generate this cloud of electrons and positrons. So the dynamic is quite rich, and understanding all these interplay is one of the challenges for the field. One of the critical components to understand these processes are particle in cell simulations. And particle in cell simulations, they come, well, there are many different codes. They come in different names, but the essential algorithms are described here. So you have particles that are moving in a grid, that are advanced according to the Lorentz force. They deposit their current on the grid. The current serves as a source for Maxwell's equations. This allows us to determine the electric field and the magnetic field, and the advanced electric field and magnetic field in time. And then these electric fields and magnetic fields are then interpolated on the position of the particles, and then we can advance the particles. Of course, as soon as we go to higher intensities, we need to supplement Maxwell's equations and the Lorentz force equation with other processes, namely photon emission, for which there is leads immediately to a change on the momentum of the particles that are emitting the photons. And this emission needs to be emitted with some probability. So this creates extra particles, in this case photons, and then the photons themselves, they need to propagate inside the simulation window. And they eventually interact with the background fields and lead to generation of new particles. Of course, if the new particles are charged particles, they need also to deposit their current. So you can see this is a very nice way to add extra physics to the particle in cell loop and include these processes. course, there are many open questions on what are the best strategies to do this, what is the accuracy of these techniques, but this has proven quite a useful approach to understand the plasma dynamics under the presence of very intense lasers. There are a number of challenges that are numerical challenges that I'm not going to cover here. But this by itself, from a numerical point of view, this is one of the frontiers, which is really triggered by the vision of having ultra high intensity lasers that can take us to this frontier. So the results that I'm going to show are from OSIRIS, which is a code that has been developed for more than 20 years between UCLA and IST. And I'd just like to take this opportunity just to advertise that now there is an open source version that you can just look it up and download and try it out and actually use it for your own research. Of course, this is what I've shown is just an example, but there are many papers that have explored this setup, and this setup is extremely rich. I'm just going to show another a few examples just of the diverse physics that you see just by instead of looking at just at two-dimensional simulation, just three-dimensional simulation, just looking at the lasers with different colliding with different polarizations, and we can just appreciate just by looking at the movies the richness of the physics that is involved in all these scenarios. So this is definitely one of the most exciting frontiers. Of course, the intensities that we are talking about here are very extreme intensities. And before we reach these intensities, probably there are regimes where the plasma dynamics is affected by these QED processes. And this is one of the most recent avenues for our research. It's actually to understand as we go from the classical regime to the quantum regime, what is the physics, the new physics that might come into play that modifies the plasma dynamics. I would like to tell you a little bit about this. Of course, there are other QED processes that might come into play. And this just shows you the variety of all the processes that can be important as we go to much higher intensities, with relativistic fluid velocities even higher for the plasma. And this also means that we need to complement our numerical simulations with this process. So we are definitely just starting to explore many of these processes with ultra high intensity lasers, and the future is even brighter than the lasers that we are using, because as we move up in intensity, many of these processes start to play even more important roles. What I want to show you is something that is really at the core of many of these processes, which is the imprint of radiation reaction on the distribution functions of plasmas, and how these imprint can lead to the onset of electron scale kinetic instabilities. So this is a really fundamental plasma physics process, but surprisingly, when we start to think about this carefully, we really come to the conclusion that it can actually have an important role when we start to take into account these effects of strong radiation that naturally occur whenever we have the interaction of plasmas with strong fields. The most simplest possible configuration is the one that we are going to explore. So we are just going to consider the plasma dynamics described by the Vlasov equation with an extra force, and this extra force that I'm having here on the Vlasov equation is just a radiation reaction force. If you remember, on the particle in cell loop, there was an extra term that was added to the Lorentz force. So this is actually this term here, that I'm going to assume its classical version. What is critical here on the description of this force is this is a non-conservative force. So this brings significant modifications to the plasma dynamics. So the radiation reaction force of course, there's been a strong debate about what is the structure of the radiation reaction force. There are a number of papers on this, but we are using to understand the physics here, the leading order of radiation reaction force according to the line law and Lifshitz formulation. And we are even considering a more simplified scenario just to illustrate our point, which is a scenario where we just have a plasma in the presence of very strong magnetic field. In these conditions, the radiation reaction force is very simple. But when we look at the radiation reaction force, we quickly realize that there is a nonlinear dependence on the perpendicular momentum of the electrons that are gyrating in the very strong B field. So this means that electrons with a higher P perp will radiate strongly than the ones with the lower P perp. Actually, it's possible to have an analytical solution for this equation, which is quite nice. And this is something that makes a very nice connection with work on the study of runaway electrons in fusion plasmas. And similar solutions have been recently found in papers published by another group. I take also the opportunity to advertise that the paper describing this, authored by my student Paulo Alves, as the lead author, has just appeared in PRL this week, so we should just look it up. There's a very nice picture to illustrate it, and I'm going to show a couple of movies just to trigger your enthusiasm for this paper as well. So what is interesting is that with this model, analytical model, we can actually now look at the evolution of any distribution function in the presence of radiation reaction in this model. And what is interesting is that if we play a movie starting with a Gaussian, a Newton distribution function, or a power law, or even a constant negative slope, what we quickly understand just by propagating this distribution function according to this formula here is that the distribution function quickly develops regions with where the gradient or the derivative of the distribution function along P perp is greater than 0. So this means that in these regions the plasma is going to be unstable. So this is quite surprising, because you don't expect starting a plasma from a situation of plasma which is as a Gaussian distribution function or a Newton distribution function, so it's in equilibrium or close to equilibrium, that it will develop these features that will render the plasma unstable. But this is a natural consequence of radiation reaction. Just to illustrate the physics, I will just show full-scale particle in cell simulations. We are just showing here the momentum. So this is P1, P2, P3. The plasma is initially hot, and here you're going to see the evolution of the kinetic energy in the energy in the plasma and the radiated energy as cyclotron radiation. Here is also a snapshot of the emitted radiation. So as I've just described, when the movie is not playing very, this is not playing very well. I'm sorry about this. Let's see if the movie plays when it reloads. It plays a little bit better. Yes, okay. So the plasma is gyrating in the B field. The B field is pointing along the P2 direction. And as predicted by the theory, you form a nice ring. So you start from a Gaussian. The distribution function is strongly cooling. So the plasma is losing its energy. You start to see some radiation, but it's not very strong. And now, if we let it continue, oops. Having a small technical problem here. I'm sorry about this. I thought this was okay. I will describe what's happening. So if reach at this point, we already have the ring form, and then if we let it run for a longer time, what we will see is that the particles will start to bunch on this direction, And as they bunch, they will start to radiate coherently. And you'll see very clearly on this movie, you will see coherent radiation at low frequencies. It's also clear as time evolves that a fraction of the plasma energy, close to 0.1%, is actually radiated as radio waves. So which shows clearly a path to generate coherent radio emission, starting from a plasma where radiation reaction is done. Of course, this is quite exciting, but it's quite hard to reproduce these conditions in the lab. These very strong magnetic fields, and even with laser fields and this configuration, it's still very hard to get to these conditions. So we've been trying to reproduce in the laboratory a little bit some of these instabilities driven by rings. This is motivated exactly by what I was stating. It's very hard to probe the interplay of QED with plasma physics in the laboratory. There are a number of papers that have explored QED effects in hole boring. So on the leading edge of the interaction of the intense laser with the solid target, there are some corrections that come into play. When a solid target is irradiated from two sides with two very high intensity lasers, one can also get evidence for the role of QED effects. And also recently we started to try to understand if high harmonic generation was modified by QED, and then you can actually see that on the emitted spectrum of high harmonics there are corrections due to quantum electrodynamics when these are taken into account. But it's still very hard to generate conditions, laboratory conditions, where the plasma dynamics is clearly affected by QED effects. So what we've been trying to understand is, can we explore these instabilities, like ring-driven instabilities in the laboratory in a different way? And it's definitely possible. And we have, for the work that I'm going to show, we have looked for inspiration in very nice recent papers by the group at UCLA that has been using laser ionization as a platform to tailor initial plasma kinetic conditions. These are pictures from recently published papers where you see that you send in a laser pulse with circularly polarized light, and due to the ionization process, it's possible to generate rings in the momentum distribution. Okay, so again, this is laser propagating. This is the transverse momentum distribution of the electrons, and due to the conservation of canonical angular momentum, it's possible to show that the ionized electrons are the electrons that are generated from ionization of background gas will form a ring. So this has been explored, and very nice recent results by the UCLA group in collaboration with teams in Beijing that have used this platform to look at the onset and the saturation of plasma microinstabilities. They've been looking at the current filamentation instability, and they've done very beautiful experiments at the ATF facility showing precisely the evolution of plasma filaments driven by the current filamentation instability. So what we've been trying to understand is going a little bit beyond this. So these are for setups that are unmagnetized. So we've been trying to understand, can we drive and design these experiments to study the onset and the saturation of kinetic plasma instabilities in magnetized plasmas, in particular to look at what happens with these rings in momentum space. And to do this, we've been exploring different scenarios, and this is one of the most obvious. using state-of-the-art but existing lasers by sending a CO2 laser pulse through a background gas target, and in the presence of very strong magnetic field. So these are just for illustration purposes. We have a publication that is in preparation that demonstrates that these numbers can be relaxed, but with these parameters is much cleaner to see all these effects. And so what we want is just send in the laser. The laser is going to ionize the plasma. It's going to generate a column of plasma that is illustrated here in the grayscale. And now, if we look carefully at the distribution function that the laser is leaving behind, we see these rings. Okay, so we have these nice features in momentum of these rings. It's quite interesting that, as I mentioned, there is a strong B field. The B field actually suppresses some of the instabilities that were studied in previous works, and guarantees that the instability that we are looking at, this electron cyclotron maser instability, is the one that is going to dominate this type of setup. And so it's possible to do 2D and 3D simulations of this, and this is one of these examples that serves to illustrate the different physics at play. So we have a laser pulse which is circularly polarized. It generates a wake, which is the structure that we see here in the back. This is the region where this electron cyclotron maser instability starts to grow. So in this region, we have the ring. The instability starts slowly to grow, to have this bunching in momentum space, starts to grow. And we have, as a result of the growth of the instability, we have both longitudinal modes that are generated, and we have transverse electromagnetic modes that are also generated and that escape the plasma. And we've been examining in detail the physics of these transverse modes that escape the plasma. This can also be done with controlled simulations, and this is quite it's a quite nice way to look at these setups, where we just initialize our ring in momentum space, and then we look at the evolution of the instabilities. And what is very interesting is that this is an excellent setup to look into these modes, and there is an excellent agreement between what is predicted by the theory, which is modes growing at harmonics of the cyclotron frequency, and what is predicted by and what is observed on the simulations. So we clearly see this coupling between the rings that are generated and then the evolution of these rings and these and the generation of this radiation. So this is quite exciting and show us that we can mimic in the laboratory these type of kinetic distribution functions that are naturally generated on these scenarios where we have strong radiation reaction. So I think I would just like to summarize. I think I'm reaching my time here. What I would like to share with you today is that with the kinetic plasma at ultra-high intensities share common methodologies with other extreme plasma conditions. This is very exciting because some of the physics that we can explore with lasers are also relevant for these relativistic astrophysics scenarios. Of course, not all the things are the same, but some of the techniques that we use to address one scenario can also be transported for the other scenarios. The interplay of plasma kinetics with QED processes introduces qualitative modifications. And what I've just highlighted is that even the most simple one, which is radiation reaction, can drive unstable electron distribution functions. And this also can have consequences in other processes, in plasma physics processes, for instance, reconnection. And there's definitely the opportunity to explore in the lab some of these relevant configurations, either with directly driving, for instance, cascades or other processes, but probably still we are still a few years before this can become reality. But before that, one one can conceive scenarios where we reproduce the plasma distribution functions in the laboratory, again using lasers and using the nice properties of controlling ionization and plasma generation, to study some of the kinetic instabilities that are also present when we consider QED processes and all that interplay with the collective plasma dynamics. So this is what I wanted to share with you. So thank you again for the opportunity, and congratulations again on the 10th anniversary of the journal. Thank you.
And thank you, Professor Silva, for your sharing on plasma kinetics with intense laser. And we really appreciate your willingness to join this symposium at such late time in Europe. So thank you, and we definitely wish you a good night. And for our audience on Zoom and also on the live stream platform, if you have any questions that you wish to discuss with Professor Silva, I think you could reach him by email. So our second lecture today will be presented by Dr. Paulo Alves. He will be discussing about the application of machine learning in laser plasma interactions. Dr. Alves is currently an assistant professor at UCLA. His interests span a broad range of topics, from understanding how the most energetic particles in the universe are accelerated, to harnessing plasmas to control and amplify ultra-intense lasers. His research combines analytical theory and the state-of-the-art numerical simulation to understand the nonlinear and multi-scale dynamics of plasmas in this system from the first principles. And Dr. Alves is also the member of advisory board of the Journal of Plasma Physics. Welcome, Dr. Alves.
Thank you very much. Thank you for the invitation, and good morning, good evening, and good afternoon to everyone. First of all, can everyone see the slide I'm presenting? Okay, great. So thank you again for the invitation. I'm excited here to tell you a little bit about what myself and my collaborators have been thinking about with respect to you taking advantage of machine learning to help us understand, stimulate, and predict plasmas in more accurately or more profoundly. So. Before I begin, I would like to first acknowledge that I'll be presenting work that was carried out with many of my colleagues. In particular, I would like to highlight my colleague Frederico Fuse and Jason Shu from SLAC, and many other colleagues from Stanford University with whom we have a project that I'll be describing here. So the motivation of this work is that we are interested in understanding and controlling intense laser plasma interactions for various applications. And here I highlight two specific applications of great importance, taking advantage of intense laser radiation to drive nuclear fusion here on the left, and on the right-hand side, we're interested in there's enormous possibilities of taking advantage of intense laser solid interactions to produce secondary sources of charged particles and radiation for various technological and scientific applications. The challenge in all these systems is that we're interested in order to realize and take advantage of these technologies, to bring them to fruition, we have to understand how to control lasers interacting with plasma. And the challenge in many of these systems is that the physics is highly nonlinear and is multi-scale. And this is what poses tremendous challenges to our understanding of these systems and tremendous challenges to modeling these systems. Here on the left, for instance, in inertial confinement fusion, the physics that governs how the laser couples to the plasma is dictated by the smallest dynamical processes that occurs in plasma, so the so-called plasma kinetic scale. And this eventually has to couple to hydrodynamic motions of the plasma. You ultimately drive implosions, which is, these are hydrodynamical processes that ultimately compress the fuel and trigger fusion. So these interactions, this physics spans very many spatial and temporal scales, and modeling these systems is extremely challenging. So these challenges have driven a lot of interest in developing reduced models in order to simulate these problems. And here's a diagram, a very helpful diagram that describes the suite of reduced descriptions that's widely used to model intense laser plasma interactions in the context of inertial confinement fusion. So here at the smallest length scales, when we understand how intense laser radiation interacts with the plasma, with the ICF fuel, we utilize kinetic bond. Indeed, as when this intense laser radiation couples to the plasma, we drive distribution functions that are far from equilibrium, and the most appropriate description for the dynamics at those scales is using kinetic descriptions, Pick or Vlasov or Vlasov-Fokker-Planck. And as we move to progressively larger scales and longer time scales, there are other components here that are important in order to model the full dynamics. In particular, at the larger scales, we have what are called radiation hydrodynamic models to model the implosion. Now, there is a lot of effort in trying to couple these different descriptions, improving these individual reduced descriptions, and then coupling them together in order to have self-consistent, holistic models of these processes. But these reduced models are still based on analytic theory that has very limited ranges of validity. So we've been interested in understanding if we can take advantage of machine learning tools to develop accurate and computationally efficient reduced descriptions of plasma, but based on data, and in particular data from first principle simulations, because these first principle simulations can capture all of the physics that of interest. So we're interested in understanding how we can use machine learning for these types of tasks. So in this talk, I'd like to talk about two different angles that we've been thinking about. Here on the left, I'm going to tell you about our efforts in utilizing machine learning techniques to distill interpretable reduced partial differential equation models from the data of first principles kinetic simulation. And these reduced descriptions not only offer us, by being interpretable, not only offer us insight into complex plasma dynamics, but we can take advantage of these to simulate plasmas more efficiently. In the second part, I will tell you a little bit about our efforts in utilizing machine learning to couple different descriptions of plasma, to couple hybrid descriptions, fluid and kinetic models, and how we've used this in a specific problem, in a intense laser solid interaction problem, in particular an ion acceleration problem. So these are the two problems I would like to discuss here today. And so I'd like to begin first with the possibility of inferring reduced PDE models from the data of first principles simulation. Before I begin, I want to briefly reiterate that these first principles simulations that I've been exploring are based on the particle and cell method, as Professor Luís Silva just presented in the previous talk. This algorithm provides a self-consistent description of plasma dynamics. It describes the motions of individual particles in plasma and captures their motions according to their self-consistent electric and magnetic fields. And so from the point of view of building reduced models, starting from the data of these kinetic simulations is a great starting point, because these do capture the most fundamental aspects of plasma. And so to illustrate the kinds of things we can do with these machine learning techniques, I'm going to illustrate this with this example showing nonlinear plasma dynamics in phase space. So here we've got a visualization of the plasma phase space in one dimension and one velocity coordinate here in phase space, and we've got two counter-streaming beams of electrons here. So we have an unstable plasma configuration here. This is an equilibrium configuration, but it is an unstable equilibrium. Due to small perturbations, we see the development of an electrostatic instability. This is known as the two-stream instability, and this gives rise to these complex motions in phase space of the plasma distribution function. So we were interested in understanding if we could utilize machine learning tools to infer the governing equation of this distribution function, this orange cloud that I'm showing you in phase space, directly from this data. Now we know from kinetic theory that the governing equation of this distribution function in phase space is the plasma kinetic equation, the Vlasov equation. So this was a good problem to first see if we could infer this governing equation. And the strategy by which we're doing this has been inspired by very nice work done by some colleagues at the University of Washington, in particular Nathan Kutz and Stephen Brunton. They have which have proposed a method based on sparse regression to infer interpretable ordinary and partial differential equations. And we've been extending this in order to apply these to plasma physics. And so the technique is rather simple. The idea is that we have here data of the dynamics we're interested in learning about, or in the dynamics we're interested in describing. So we have snapshots of the distribution function evolving in time. And we've got the self-consistent electric field as well, which is represented by this black curve. And now the idea is that we can sample the data at these different points. And what we're interested in understanding is we want to understand what is the equation governing the distribution function. So the idea is that at each point we can infer the rate of change of the time derivative of the distribution function, and we can measure this directly from the data. And we can construct a column of measurements of the rate of change of the distribution function. Then the idea is that we are looking for the right-hand side terms that describe this distribution function, the evolution of the distribution function. And so we construct a large library of possibilities, of possible candidate terms. And in this case, this is made up of all of the physical observables of this problem. So the phase space coordinates, x and v, the electric field, distribution function. We use polynomial combinations of these terms, and we also include derivatives of these quantities. So spatial and velocity derivatives of the distribution function, for instance. And we combine these to form candidate terms to describe the distribution function. Now, the idea is that we have to solve a regression problem here to identify which of these terms best describes the data. This turns out to be a challenging problem, and the key insight that enables one to pick out the correct governing terms is by utilizing a sparsity promoting regularization. The idea is that we are looking for the simplest arrangement of terms that best describes the data, and that's enabled by imposing a penalty on the complexity of terms, on the number of terms. So this is a penalty on the so-called L0 norm of this vector of coefficients. And when one does this, one identifies the correct governing PDE, and that's observed over here. So we identify the advection in space and advection momentum terms of the Vlasov equation, and we can compare it here with the true Vlasov equation. There is, however, a large error here in these coefficients. These should have been exactly -1 and +1. So we're identifying the right terms, but these coefficients are very inaccurate. And it turns out that this inaccuracy is coming from the fact that this data that's originating from particle and cell simulations is noisy. So there are discrete particles in the system, and when we construct these distribution functions, there are fluctuations associated with the presence of discrete particles. And so we've introduced algorithmic innovations that allow us to overcome these problems. And I would just briefly like to mention that we utilize an integral formulation. So we've developed an integral formulation strategy. So instead of identifying our governing equations in their differentiable form, we identify these governing equations in their integral form. So we essentially evaluate all of these candidate terms, all of these observables. We evaluate them in compact volumes in the data and average and integrate over those volumes. And when we utilize this strategy, we identify these governing equations very accurately. So here we've got we've correctly inferred the loss of equation with very high accuracy compared to that previous method. And what's very interesting here is that we've identified, this is an illustration of identifying a governing equation that was not explicitly solved by the simulation. So we were solving different equations, and the particle and cell method solves a different set of equations, and we're able to infer an emergent equation of the distribution function utilizing this method. And so we've taken this beyond inferring kinetic equations. Indeed, we're interested in utilizing this to discover reduced descriptions of plasmas. And so we've demonstrated that we can infer the full hierarchy, the fundamental hierarchy of plasma equations. So from kinetic to multi-fluid equations to single fluid magnetohydrodynamics. And here I'm showing you an illustration of recovering the single fluid magnetohydrodynamics equations from particle and cell simulation data. This is data of the propagation, of the formation and propagation of a collisionless magnetized shock. And here I'm showing you the inferred governing equations. These are the equations of the moments of the distribution function, so the continuity, momentum, and energy equations that describe the plasma, that provide the single fluid description of this plasma. And here I'd like to point out that this integral formulation strategy that I just mentioned was crucial to do this. One was not able to identify these governing equations correctly by evaluating using the initially proposed method. Now, there is in order to make use of these equations, I would like to point out that these are exact conservation laws. This is not a closed system of equations. There's a heat flux that one has to learn. And so we have to solve a closure problem here. We have to find a closure model for this problem. And this is precisely an area that I believe machine learning has a lot of potential to contribute to. Let me just show you how this tool automatically gives you insight into how we can utilize insight as to how we can close the system of equations. So here I'm showing a curve that represents the Pareto curve obtained for this energy equation, this MHD energy equation. And so we're looking at a family of models that was identified by this procedure. And we're looking at this family of models, and we're looking at their accuracy of these models. So this is model accuracy versus complexity of these models. And this complexity is measured in the number of terms of these models. And here what we see is that initially, if we can start out with very complex models with many terms, with 50 terms. As we progressively find simpler models, we do not see a significant decrease in the accuracy until we get to a special point. We find this elbow in the accuracy complexity curve. This elbow marks this optimal trade-off between accuracy and complexity, and this tells you this is the system of equations that best describes your data, and this indeed corresponds to the full energy equation. What's interesting is that if we look to the left of these models, we see a hierarchy of progressively simpler models with progressively less and less terms. And these approximations are completely interpretable. So we understand exactly the meaning of these individual terms, and we understand what approximations are being done. For instance, for this particular data, we were able to see that Joule heating was the least important effect, followed by off-diagonal terms in the pressure tensor. After that, it was neglecting pressure and anisotropy, and only finally, the simplest term was obtained by neglecting heat flux. And when one neglects heat flux, you're dealing here with the widely used adiabatic closure that's widely used for many problems. And here we're showing that this data-driven approach was able to recover this adiabatic closure. And now, but in the future, we would like to discover improved fluid closures, and so we're working on this. But at the very high level, what I would like to say is that these tools, I'm very excited about these tools because there is a suite of high fidelity numerical simulations from particle and cell, Fokker-Planck, gyrokinetics, molecular dynamics, that are all used to target different problems in plasma physics, in ICF, in intense laser solid interactions. And we're developing a general data-driven model discovery framework that can take advantage of the data coming from these simulations and allow us to distill, to extract improved reduced plasma models. And these may manifest in the form of improved kinetic fluid closures, reduced models of laser plasma interactions. And once we have these types of reduced models, we can integrate them into more macroscopic models and do integrated holistic modeling of many scenarios of interest. ICF is an example, but there are many other scenarios of interest, laser-driven secondary sources, for instance. Now, with the remaining time I have, I'd like to tell you a little bit about a different strategy that we've been exploring to take advantage of machine learning to enhance modeling of laser plasma interaction. And so we've been focusing on this problem of intense laser solid interaction. And in particular, we're interested in these intense laser solid interactions can be used to accelerate ions, and so therefore can result in a laser driven ion source. And in these problems, it turns out that there is these problems are extremely challenging to model from a kinetic from a fully kinetic point of view. And they have the following characteristic. It turns out that only a small fraction of particles are accelerated. And that small fraction of particles carries a significant fraction of the laser energy. The majority of the particles in these systems remains quasi-thermal. They are these background particles. So here we're taking this represents a phase space plot, a phase space diagram in this region, and we're seeing that the bulk of the particles remain Maxwellian, and only a small fraction of the particles is undergoing complex dynamics from interacting with the laser. So there's a small fraction of particles that is interesting to model. A large fraction can be approximated using a reduced description. And when one does fully kinetic calculations of this, one is using a lot of computation to describe this thermal component. So it's very, very inefficient. So we're interested in understanding how we can improve this. One of the strategies to improve this is to use hybrid models. So to utilize a kinetic description where necessary and a fluid description in components of the plasma that are approximately Maxwellian. And so these hybrid descriptions have been around for many problems and for a long time. And the idea is that this provides a route to achieving efficient descriptions of plasma dynamics in these scenarios. And so the idea is that one has to use, for instance, a particle and cell description to advance kinetic particles in time, use fluid equations to advance the fluids in time. They couple to each other through Maxwell's equations, through the currents that they produce. But there is a critical part here where in many of these scenarios, there will be a fraction of the background fluid that will be promoted to a kinetic description. And finding reduced descriptions that capture this is a challenge. And to the best of our knowledge, this has been under development. So there are these three critical elements of the hybrid method. It's self-consistent coupling between these two populations. This is something we have to get right. An accurate description of the plasma background, so of the background plasma using a fluid description. So we need to find appropriate closures for these fluid moments. And we need to find or to learn an injection, a prescription for injecting particles from fluid to to a kinetic description. And this is a process whose physics is not well understood. And again, we think that machine learning can offer an interesting approach here. And so this is the strategy that we are adopting. So at any point in time, we have a group of kinetic particles. These particles are particles that we have accumulated. At any point in time, we also have newly injected particles. And at any point in time, we also have fluid particles. So we always have these three categories of particles. The idea is that kinetic descriptions, that these kinetic particles will be advanced using a PIC solver, and the fluid descriptions will be applied to the background fluid and advanced using a fluid description. And at each point in time, once we advance these things in time, we have to take into account how a portion of this background fluid, we have to predict what portion of this background fluid is promoted to a kinetic description. So we need to do this separation. So this is what we've tried to do using machine learning. So in order to do this, what we do is we carry out fully kinetic simulations of this interaction. And then we construct data that allows us to separate thermal from non-thermal components, and that or kinetic components from a fluid component. And that is what I am showing here on these diagrams. Here on the left, I'm showing the phase space of the electrons, and in green we see the thermal components of the electrons, and in blue we've developed an algorithm to identify what are kinetic components, energetic components of the electrons. So we have developed a heuristic algorithm to separate these two components, and we've done the same for ions. Having these two components now separated, we now have the data in order to learn a prescription for how these for the injection of these particles based on local plasma and electric field conditions. And this is highlighted here. So we've utilized neural network models to learn these prescriptions from data. In particular, we've used neural network models to learn how to inject electrons, and it turns out that these injected electrons are occurring at the front surface of the target, and we can predict these very accurately. And we can also predict the injection of ions at the front surface of the target. In fact, we predict the full probability distribution of ions and electrons from the local plasma and field conditions. And now we are working to put all of this together to build self-consistent hybrid simulations of these interactions. So the idea is that we will do a PIC advance of the particle, a fluid advance of the fields of the fluid quantities. After these has been advanced, we do this so-called injection phase, which we have learned, and this process is captured in a machine learning model. We learn the probability distribution of particles that are injected, and we sample from this distribution. Once we sample, we generate new particles. We remove the mass, momentum, and energy of those particles from the fluid, and then proceed with the standard loop: deposit the currents of the kinetic particles and of the fluid, advance the fields, and repeat this loop all over again. So we're currently working on this aspect of the problem. So to briefly summarize, we've developed machine learning tools based on sparse regression to extract models from the data of first principle simulations. These are reduced models that can give us insight into complex plasma physics. They can be used as a tool for theoretical plasma physics, and I think these models offer a promising, or these tools offer a promising route to developing computationally efficient reduced models of plasma dynamics for multi-scale applications, including intense laser plasma interaction. And then finally, in this last example, I tried to show you that there are interesting aspects here where we can utilize machine learning to couple reduced description. So applying machine learning to well-established numerical techniques, fluid and kinetic simulations, and there's an aspect here that is unknown, which is this injection, how to promote parts of the fluid to a kinetic description. And this is an area that we've identified machine learning could help. And our results seem to be very, very promising here. And so we're currently working on building these self-consistent hybrid simulations. And just as a final note, these machine learning tools, they're not restricted. They can be broadly applied to other areas of plasma physics, in particular space and astrophysical plasmas. And this is also an area that I'm very interested in exploring these types of tools. So thank you again for the invitation, and congratulations again on the 10-year anniversary.
Thank you, Dr. Alves, for your interesting presentation, which was very impressive, and we really appreciate your support on this event at very last minute nature. And now we may have time to answer one question either from our audience on Zoom or on live stream platform or from our panelists. So if there's any question, you could use the raise hand function.
If there are no questions, I have a question myself.
Oh, okay, sure.
I have a question for Luís. In these distribution functions that are being driven out of equilibrium due to radiation reaction, so I was just curious. Then, what do we know what these ultimately relax to? So then, in the movie, we saw what they relax to before the onset of this velocity space instability, right? These kinetic instabilities. But what do they ultimately relax to?
Yeah, what we have seen is that they will there's a bursty behavior. Because the first there's this bunching, then there is radiation, then there is further then they relax again to something like a ring. But then if there is enough free energy, the ring keeps contracting. Eventually it will get to a situation where radiation reaction is no longer important, then it will thermalize like a Maxwellian. But it goes through a kind of a cyclic bursty process where you generate a ring, then you have velocity bunching, then it radiates, then it forms again the ring and might constrict. So there are a few time scales that, depending on the strength of the B field and the initial thermal velocity, are at play. So it's quite a rich behavior, and we are now exploring this bursty behavior. Yes, it's very interesting.
Very cool.
Yeah.
Thanks.
Okay, so let's now move to our panel session today to talk about the two journals. Our guest for the panel session will be Professor Xiaoyan Liang from Shanghai Institute of Optics and Fine Mechanics, who is the editorial board member of High Power Laser Science and Engineering. She will be introducing about the journal. And another guest today we have is Professor Troy Carter from UCLA, who is the associate editor of Journal of Plasma Physics, who will be also talking about the journal. So welcome, Professor Liang and Professor Carter.
Okay, thank you.
Thank you.
Okay, next step, I will give a talk. And first I will share my slide. Okay. Good morning and good afternoon and good evening. On the behalf of the journal, I will give an introduction of our Journal of High Power Laser of Science and Engineering. And my introduction will give in this sixth part. Firstly, I will introduce the journal management. Our journal is managed by Chinese Laser Prize, Cambridge University Prize, and the editorial board under the lead of co-editor-in-chief. Our co-editors-in-chief is Professor Colin Denson, Professor Chen and Professor Michel Cabell. The duty of this CLP, editorial board, and the Cambridge University Prize is listed here. For example, Chinese Laser Prize is mainly responsible for to manage the submission systems Scholar One and promote the journal and papers, invite papers, communicate with the editorial board and others. For editorial board, it's responsible for to handle manuscripts as a topical editor, invite high quality papers, promote journal and papers, recommend experts to join editorial board, and organize special issues. For Cambridge University Prize, is to be responsible for production of papers, manage the journal's homepage, and promote journal and papers. Our aims is try to uncover the underlying science and engineering in high power laser related fields. The article types contain research articles, review papers, letters, perspectives, and commentary. Our scopes include laser technology, laser facility support technology, laser interactions, and the secondary source generation. Okay, from this figure, we can see that our journal is doing well in recent years. The impact factor is keep rising, and this indicated that the journal has more and more readers. 2 years ago, the impact factor is rise to nearly 6. For the last year, is around 5. So this is because we have a very strong team, especially our co-editors-in-chief, Professor Michel Campbell, Professor Colin Denson, and Professor Chen. Our editorial board have 28 members from 12 countries. Here we list some outstanding board members of our journal. All of them are the international expert in this area. Meanwhile, we also established the earlier career editorial board of our journal in 2020. This initiative is to bring together a number of talented physicists, engineers who are a few years after completed a PhD. This board, which would operate largely virtually, and would advise on the future direction of the journal, suggest ideas for promotion, initiative special issues, contribute to the biennial conference organization participation and encourage submissions to the journal. Until now, 28 young talented experts from 11 countries have joined the early career editorial board. Here is the outstanding members of the early career editorial board, especially our co-auditor of Miss Charlotte Palmer from Queen's University, Belfast of UK. A link to the journal's editorial board would be provided through the coordination of the early careers board by Dr. Charlotte Palmer. And here is some outstanding members. And until now, our journal has published more than 450 papers from 31 countries in the past years. Especially in the last year, readers from 140 countries viewed the papers based on the data of CAPS Web. This is the numbers according to the CAPS Web date. The publication by countries and the downloads by countries. All this number is from the last year. Recently, we have two campaigns. The one is the special ESO. This is to celebrate this fantastic landmark. So we are going to organize a special issue of the journal that will span the latest research, reviews and perspectives in the fields of high-power lasers, advanced laser technology, applications and laser components, and high-energy density physics. This is the submission deadline is the end of July this year. This marks the 10th anniversary of our journal. The other campaigns is the conference, the 5th International Symposium on High-Power Laser Science and Engineering is organized by Chinese Laser Prize. And this year, this symposium will be held on October 16 to 19 in Suzhou, China. And we believe that many of the experts will be invited to join the symposium. Also, the team is work hard to promote the quality of the papers. So the high quality papers, because the high quality papers are very key for our journal, and which aims to bring novel ideas and important achievements to readers of this community. We have multiple ways to promote excellent papers. For example, we posted very recent and outstanding publications on WeChat like this. Also, we take care about the email campaigns, also promotion the journal on conference. Meanwhile, this category of community brings together news of conference facilities, latest achievements, and so on in the field of high-power lasers. News are regularly updated by our journal. Here, like this is the link of our community. That just like this is it contains news of conferences and facilities and appointments. Also contain the latest research results. Besides, international social media accounts of our journal have been established, which post news of latest research results, conference facilities in high-power laser fields. And experts and statistics are welcome to follow our social media for the latest news in the community. Just like in Twitter, we have our accounts in LinkedIn, also in Facebook. All this is a very this social media account are very welcomed. Also, you are welcome to join the journal as board editors, reviewers, authors, and welcome to our recent campaigns. Thank you very much.
Thank you, Professor Liang, for your comprehensive introduction about the journal. And for our audience, you are welcome to follow the social media account for high-power laser science and engineering, for example, on LinkedIn or Twitter or WeChat. And I wonder if you have any question to the journal, you can raise it up to Professor Liang, so she will be answering. And if no question for now, let's welcome Professor Troy Carter to introduce about our another journal for today's symposium, Journal of Plasma Physics.
Okay, thanks. Let me share my screen here. Let's see. Try it this way. Work. There we go. There we go. Good. Okay. All right. I'm glad to be here to represent Journal of Plasma Physics. At first, say congratulations for 10 years for high power laser science and engineering. That's a great achievement. I'm here to advertise another Cambridge University Press involved journal, in particular Journal of Plasma Physics. We view this as the place to publish a plasma physics result that you're really proud of. And there's lots of features that are advantageous for this journal. Doesn't cost anything to the author to get it published. No page limits are involved. We believe it's the most beautiful format possible for a journal in that it's a single column, good for e-reading and for beauty, as it says. The copy editing is done in the UK. And so we like to say we're not going to ruin your algebra, but we will improve your grammar. And I know I need that when I'm writing a paper. There's easy access to NASA ADS as well as to the archive. We encourage archiving of papers. We also highlight highest cited papers and featured articles every month in every issue. And I'll show a few of those that are in this area a little bit later. And of course, a feature that's true for this journal as well as for high power laser science and engineering is you're interacting with a real editor of your choice. And so you have some of the most distinguished plasma physicists in the world on this editorial board that are there to take care of your article and make sure they choose good reviewers. And so the editors of the journal are Bill Dorland at the University of Maryland, Alex Chikichin at University of Oxford. Plasma physics is an incredibly intellectually diverse field, and there's a wide variety of areas that we cover, including high energy density plasmas, laser plasma interactions, and inertial confinement fusion. But you can see your editorial board here for this journal, including myself and Luís Silva. We also, like HPLSE, have early career advisory board, and Paulo Alves, who gave a talk earlier, is a member of that editorial board. So we use them to help identify new trends and new directions. They also run our social media accounts because they're much better at it than some of the older folks on the editorial board. So again, I'll just reiterate that the advantage of Journal of Plasma Physics for your plasma physics paper, you're going to have a high quality editorial board that will caretake your article, will read it first of all, so you know somebody is going to read the article and make sure it has the right kind of review. All right. JPP is a long-standing journal. It's been around for decades. But it's been a recent project of the editorial team to really turn it into one of the leading journals and most high impact journals in the world in plasma physics. And we've now seen that realized. The impact factor has risen steadily over the last decade to the point now where we're a higher impact than some of the other journals that are well known in plasma physics, physics of plasmas in the US, plasma physics and controlled fusion also in the UK. And we anticipate that this will continue. So we're getting high impact articles and bringing readers and lots of good papers to the journal. I mentioned earlier that we have featured articles. So every issue, the editorial board will look at the articles that are there, decide which ones we want to provide for free access to anyone on the internet. We also look at our highest cited papers and try to make sure those are freely available. I just pick out a few that are relevant to the area of today's discussion: laser plasma and laser matter interactions. And here you have 4 recent publications at JPP that are featured articles and are available to you to see for free. We're also very interested in growing our interaction with China and Chinese authors. It is true that it has been a strong growth in Chinese submissions and publications in JPP over the last 4 or 5 years, that you can see here, up to about 13% of publications in JPP. And China was the second highest submitted country in 2022. So we're very interested in interacting with Chinese authors, and I'm very happy to answer any questions or to follow up with you after this. Feel free to email me or the editorial board if you have questions about the journal. So I'll be brief. I'll just end with the same slide. Just say that we would welcome your submissions into this journal in this area of laser matter interactions, inertial confinement fusion, and related areas. I'll point to the website here at the bottom and encourage you to reach out to me and ask questions now if you have them about the journal. Thank you very much for your participation today.
Thank you, Professor Carter, for your introduction about JPP, and we are glad to know that JPP is welcoming more submissions from China. So if you have any question about the journal, please feel free to either ask now or contact Professor Carter later on after this symposium. And yeah, if no question for now, we can now move back to the academic lecture sessions. So our third lecture will be presented by Professor Chen from Shanghai Jiao Tong University. Professor Chen is also a member of International X-ray Laser Society and has developed a series of ultra-strong and ultra-short X-ray sources and new imaging methods with important applications. Professor Chen has published more than 160 articles and has won many prestigious awards. Welcome, Professor Chen.
Okay, so right now I'm trying to share my screen. So can you see my screen? Hello?
Yes, yeah, we can see you.
Okay, great. So it's my great pleasure to have this opportunity to introduce our recent progress concerning the laser-driven high-charge electron acceleration for nuclear applications. And thanks for the introduction of myself. Well, I don't know how to remove this. Okay, good. Okay, so my presentation include the motivation followed by the high-charge electron acceleration and enhanced the bear from our X-ray or gamma ray sources, and then the laser-driven nuclear physics, and brief summary. So at first, the motivation. The electron charge during the network field acceleration is very important, because for some very important applications, for example, the X-ray or baryton radiation. The baryton radiation is kind of laser plasma accelerator and plasma vehicular combinations. So we can call it a tabletop synchrotron radiation. This kind of radiation, the parameters, for example, the photon yield, the photon energy, or its brightness is completely controlled by the electron parameters. For example, the electron energy, the electron charge, and its oscillation amplitude and its frequency. So the electron charge is very important for the baryton radiation. And also the Thomson scattering. The Thomson scattering is a laser shining on the target and drive our electron beam. And this electron beam is correlated with another electron beam, laser beam, and Thomson scattered the radiation. So the Thomson scattering, the photon yield is also linearly proportional with the electron charge. So the electron charge, high charge electrons is very important for some applications. However, the electron beam charge have some bottleneck. For example, during our smooth accelerations of the electron beam, the matched condition, especially the matched bubble conditions, we have the limited beam charge. It's actually controlled by this formula. And in experiment, many of the beam charge is limited below than 100 picocoulomb. So how to increase the accelerated beam charge is really an important topic. We have to find another way, some other way to increase beam charge. So, besides the matched bubble condition. Of course, there are some beam loading effects with completely higher beam charge, but however, during the smoothly accelerating procedure, this beam loading charge is very difficult to be reached. So we will find some way to increase the beam charge and try to put the beam charge as close as to the beam loading effect. Our second part is high charge electron acceleration and enhanced baryton or X-ray and gamma ray sources. Several years ago, we performed this joint experiment, and we shining the high power lasers to the slightly higher density plasma, higher than the matched condition for the bubble. So in this case, we observed as this energy increase, we observed the first electron accelerated with energy higher and higher. And as this energy increase, we observed the second electron bunches with extremely high charge and energy higher than 1.4 GeV, and the charge can reach to 600 picocoulomb. It's 1.5 times higher than the matched bubble condition. And in our simulations, we observed two bubbles were combined and form a quite a long bubble. And during the two bubble combination, a second beam of electrons will be injected in the large bubble. And this second beam with high energy, high charge, and large oscillation amplitude. So it's very suitable to stimulate the strong radiation X-ray radiations. And in our later simulations to show, for example, if we choose the same data parameters as a Callisto laser at a non-Livermore laboratory, and we choose the plasma density slightly higher than the matched bubble density. So in this case, we also observed this second injection phenomenon, and the second electron bunch will have much higher electron energy and charge 10 times higher than the first beam. First beam is a more energetic electron bunch, and this second electron beam will produce the background radiations. Actually, it's a gamma ray radiation with a critical energy 1.2 MeV, maximum energy 10 MeV. So it's very suitable for the photonuclear reaction. And this simulation phenomenon is demonstrated by this paper from GIST. And when they use their petawatt laser shining on the gas target, and really observe this kind of two injections. The first is more energetic 1 GeV, and the second is a Maxwellian and with maximum electron energy close to 2 GeV, and the radiations shows almost the same as our simulations with 200 terawatt. As we know, usually in experiment, we say, yeah, it's a petawatt, but actually the effects are almost the same as 0.1 terawatt. So that's a real. So that's one way. And the second method to increase the beam charge is a DLA. The direct laser acceleration mechanisms. We through these mechanisms, we use two kind of medium. The first is clusters. Several years ago, we used argon clusters, and we got the high charge electron acceleration because the laser we used is only 3 terawatt, and we got 200 picocoulomb beam charge. It's almost 3 times higher than the matched condition, matched bubble charge, and we observed quite strong baryton X-rays. So this from clusters, by using the clusters, the DLA will be the important mechanisms for the clusters. You need to high electron charge and the larger oscillation amplitude from our simulations. The second way to use the DLA, the direct laser acceleration, is we use a solid target. We perform this experiment at the non-Livermore laboratory. We use a Titan laser shining. It's almost a petawatt picocoulomb laser with large incident angle shining on solid target with some pre-pulse, 5 millijoule. In this case, we observed quite well coordinated, only 2 degrees, and directional with laser specular directions, and the total electron charge is as high as 100 nanocoulomb. So it's also very suitable for the to generate the gamma ray Boltzmann source. And our simulations to show also this kind of DLA mechanisms for each optical circle, a group of electrons will be accelerated and combined by the self-generating magnetic field. So in this case, it will be confined and continuously accelerated the electrons with extremely high charge. The third way is we experimentally demonstrated in these 2 years, and we use actually as a SGTU 100 terawatt laser, and we tightly focus this laser to a small focus spot, and we choose comparatively higher plasma density. So in this case, we really got very strong. I mean, it's the plasma density almost 4 times 10 to 19. It's of course much higher than the magic condition, the magic bubble condition, and the beam charge we observed in our experiment with initial energy 0.10 MeV. In this case, the total charge close to 16 nanocoulomb. 16 nanocoulomb. Of course, it's much higher than the matched bubble conditions. It's only 400 picocoulomb, and it's almost the same as 10 times the beam loading effects. I mean, our simulations also show this multiple bunch injected, ionized, and injected into several weak fields, and for each field, the beam charge almost close to the beam loading effects. And so in this case, the total conversion efficiency from laser to the electrons reaches to 12%. So we're using the 100 terawatt laser in action with a high density target. We obtained tightly correlated 10th MeV electron beam with extremely high charge. This is our simulations to show the electrons continuously ionized and continuously injected to the different the followed continuous weak fields. Okay, and very recently, we also use the petawatt laser and the near critical density target, and we actually because laser power is dramatically increased, and the laser electron charge reaches to almost 40 nanocoulomb, and the actual source is 10 to 10, so it's extremely high. And well, the conversion efficiency of the Pearson X-ray generation is almost 5 times 10 to -4. And last month, our experiment using the petawatt laser and the high density gas, and in experiment we achieved a 5-degree collimated electron beam with charge 100 nanocoulomb, energy 0.10 MeV, and the X-ray flux much higher than this publication, Felicia Albert. Okay, so our simulations to shows very high charge electrons injected into the bubble, and wow, it's extremely high. These high charge electrons, we use these high charge electrons for the nuclear physics. The nuclear isomer excitations. So we see right now the nuclear excitation methods. We have the joint beam nuclear excitation, Coulomb excitation, or the gamma nuclear reaction excitation, or the NIC, the nuclear excitation where the electron capture, or NEAT. So almost all these kind of method, there is some disadvantage. because right now, almost the whole electron accelerators, ion accelerators, or the Brewster gamma ray sources, this excitation method, these facilities, their density is limited below than 10 to 16. So we think it's not so high, because if we try to excite some nuclei or isomers with very short lifetime or small cross sections, so it's very difficult to accumulate enough nuclei to be detected. So limited by the peak current of this conventional driven beam, the nuclear excitation or reaction rate of the current facilities are not strong enough to stimulate small cross-section and short lifetime nuclear isomers. Let's compare the next weak field accelerator with a synchrotron or collider. So we can see the density, the difference. This weak field accelerator can reach to 10 to 21. So it's 5 orders higher than the conventional accelerators or colliders. So this plasma acceleration is not only suitable for the new concept of acceleration accelerator, is also very suitable for the plasma collider or this plasma exciter. So we use this laser-driven electron beam for stimulate to generate a neutron source or positron source. And very recently, we optimized the beam charge and the electron beam transfer size. And we achieved the neutron source with size only 200 micron. And the neutron yield is 2 times 10 to 7. So the fluence rate we achieved in experiment is 10 to 21. So it's much higher than the expandation source. For example, in Dongguan, or the fusion reactor is only 10 to 16 or 10 to 17. So it's also very close to the supernova. So in this case, we can, to do some nuclear astrophysics study. And also this post-neutron source is suitable for the fast neutron fine absorption spectroscopy research. And we published or submitted some papers. And last year, we published this paper. We use 100 terawatt laser shining on the krypton clusters. And we experimentally and directly got the second excited state of the krypton 83, and we excite the krypton 83 isomer from ground state to the third exciting state. And then it goes to 100% to the second exciting state. And then from the second state, it will through by the decay to the ground state. And we measured the decay line, and our experiment is well fitted by the calculations. And this decay lifetime is 1.8 hours. So it's a very solid experiment demonstration the isometric state excitation. And the fantastic is after calculation, we observe this peak efficiency of this excitation is 10 to 15 particles per second. Let's compare to the BPC2 at Beijing, that electron collider. Their peak efficiency is only 10 to 10 particles per second. So it's 5 orders higher than the BPC2. So we found this is a very effective and new nuclear excitation method and can be widely used. Yeah, of course, this cluster is through the nonlinear resonance of the femtosecond pumping of the isomers. I mean, the pumping, the isomer pumping time is only 20 to 30 femtosecond. Clusters, the electron energy is not so high, so we can also use all achieved and optimized high charge electron beam with charge 20 nanocoulomb, and we shedding this beam to the indium target. And so in this case, we detected and measured the indium 115, 114, 116 is a matrix state, and the peak excitation efficiency can reach to 1.1 times 10 to 15 particles per second. It's also a very high excitation efficiency, much higher. And this electron beam is, the current is 100 kiloampere. So this is the experimental results of the indium isomer excitation via the photon nuclear reaction, gamma or gamma N reactor. Okay, and let's move to our summary. High charge electron acceleration crossing the beam loading is achieved where the oscillation injection with higher plasma density. We slightly increase the plasma density, and we got this good results. And the DLA would be important mechanism for high charge electron acceleration. We can use the clusters, we use high density, near critical density, or even solid targets with high plasma density to stimulate this DLA mechanisms to get a high charge electron beam. And the high flux particle beams or X-ray or gamma rays emission we obtain in experiment, which is very suitable for nuclear physics. This efficient isomer production method can be widely used for pumping isotopic with excited states lifetime on the picosecond or femtosecond scale. Okay, thank you for your attention. Thank you all.
Chen, for your talk, and we really appreciate your support on organizing this event with us. And now we may have time to answer 1 to 2 questions from our audience or from our panelists.
Okay. Can I ask a question?
Yeah, sure.
Okay, yeah. Professor Chen, very nice. I think it's very nice work, very systematic breakthroughs in the nuclear physics enabled by the high charge electrons. Very congratulations. And I have a question. Have you also considering this photon nuclear reaction by utilizing this high charge electrons to explore this photonuclear physics?
Yes, actually, well, here, yes, right now the nuclear excitation method, actually there is a way here. Yeah, we can shine in, I mean, we can incident the electron beam to some target, for example, the high Z target. So in this case, we can use the GDI, giant dipole resonant. We use this method and we can got quite high flux of the gamma rays, and with the gamma N reactor reaction, we can stimulate this indium. I mean here, yes, yes. For example, indium 115 and with a gamma, and then we can go to the indium 114 isometric state and or a neutron. So this is a photonuclear reaction. We can stimulate the indium 114, and the peak efficiency is slightly close to 10 to 15 particles per second. So it's also very effective. Yes, thank you.
Yeah. Okay. Besides of this, you are already shown very good results in terms of the excitation of the nucleus, right? I'm wondering, are you also considering, are there some new scheme which can fully utilizing this high peak flux of this gamma ray photons to explore or to develop some new nuclear
yes
study method?
Yes, exactly. Actually, for example, we try to for example, got the flux, neutron flux rate 10 to 22, and if we got this one here, so it's close to the supernova. So in this case, we can try to start the R process. I mean the double neutron absorption process. It's all very important research topic. Yes, in this field, for example, some high Z elements, how to form this kind of high Z elements through the slow or rapid neutron absorption process. We will, maybe the next step, try to study this study and some experiment using the super high fluence rate neutron sources. Thank you.
Okay, thank you.
Yeah.
Okay, thank you, Professor Chen and Professor Ma. Our next panelist will be Professor Wenjun Ma from Peking University. Professor Ma's current research area is laser-driven particle and radiation sources, laser proton accelerators, application of ultra-short energy carrying beams. Professor Ma currently serves as the Vice President of Heavy Ion Institute in Peking University and also the Vice Dean of Beijing Laser Acceleration Innovation Center. So welcome, Professor Ma.
Okay, thank you very much. After Professor Chen's very brilliant presentation, my talk is somehow in the same direction. I will give an give a presentation about this high efficiency generation of femtosecond X-rays based on carbon nanotube plasma, which is some new targets we developed recently. The goal of this study is also for the application of the laser-driven sources in many fields, if possible. Okay, as we know, right now the major method in the laser plasma acceleration to obtain the high-quality electrons is called the laser field acceleration. In this method, the energy of the electrons have already achieved for 8 GeV, and the energy dispersion is also well controlled below 1% possible. And based on this high peak flux electrons, there are already some demonstrated femtosecond X-ray sources. For example, by using the magnets or using the micrometer scale beta Chen motion inside the plasma, or by utilizing the Compton scattering from the driven laser and the accelerated electrons. All these methods are very promising, and this figure shows they can achieve a very high brightness. This is from this summary we can see. The photon energy ranges from a few keV to MeV level, and the source size is very small, only micrometer scale, which is very beneficial for X-ray imaging applications. And I want to mention that the peak brilliance already is close to the modern synchrotron light sources, which means that it's also already possible to start some applications by using this X-ray sources. And for example, it has been demonstrated that the X-rays from the LWFA electrons can be used for the computer tomography imaging. And this paper shows that a dragonfly can be well imaged by using thousands of shots. We can see that the quality of the image is very nice. However, we have to see right now, such applications can only be limited to very small objective. For example, in this paper, the imaging area is only a few square, maybe less than a few 1 square centimeter. And this is very, it's a very big limitation for related applications. Why we cannot increase the image area? It's because that the photons generated by a single shot is only limited to 10 to 6 or 10 to 8 photon per shot. If we want to achieve a good image quality or contrast, and we have to limit the image area. And so this is a bottleneck problem for the X-ray sources from LWFA. And at the same time, we have to see the conversion efficiency from the laser to X-rays is limited to 10 to minus 5 or 10 to minus 7, which is much lower than the modern X-ray sources like X-ray tube and the Brahms-Chalon sources and so on. The physical reason behind is that the laser plasma coupling happens in the LWFA is relatively weak. So the laser energy is difficult to be fully transferred to the plasmas. And at the same time, they have difficulties in the electron injection. So my work is recently, we demonstrate or we developed some new target made of carbon nanotubes. Such target has a 3D nest structure, and the density of the target can be less than 1% of solid density, around 1% solid density. So instead of shooting a gas jet, we can shoot such target and make sure that the laser plasma interaction can happen in the near critical density regimes. And this paper shows how the targets can be fabricated. And by using such target, we recently get a publication in Nature Photonics by demonstrating the brilliant femtosecond laser-driven hard X-ray flashes. And so now I will give some detailed introduction to this work. And one thing important thing is that whether such target can be very homogenized during the laser plasma interaction. This is a very key issue for the stability of the interaction. We, thanks to the 1D structure of these nanotubes, its diameter only a few nanometers. So we can get the conclusion from the peak simulation that such 1D very narrow tubes can be fully ionized within a few hundred femtoseconds in the raging edge of the laser pulses. And after the ionization, they start to expand and become a homogeneous plasma. In this figure that we can see, 300 femtoseconds from the main pulse, it's already very homogeneous. And this is a density gradient. As we can see, this is original density and this is homogeneous density. And the plasma scale length is only less than 1 micrometer scale. So it's a sharp-edged near critical density plasma, which is very different from the NCD plasma obtained from the high pressure gas jet, which already been demonstrated for years. Such plasma don't have the drawbacks of this plasma instability when the laser pulses interacts with the boundary of the raging edge of the plasma. And in this figure, we can see the nanotube targets, the final plasma is exactly located between the gas target and the solid target, and exactly in the NCD plasma range. Theories and the simulations have already predicted that the laser absorption in this regime is very high, can be as high as 50%. And the effective temperature is also 3 times higher than the molecule potential. And because due to this self-generated magnetic field, the electrons can be confined and accelerated to up to 10 times of the molecule potential. And by using petawatt lasers or even stronger lasers, so the direct laser acceleration happening in this NCD plasma is very efficient to generate high energy electrons. And we first made some simulations by utilizing the parameters of our plasma and a laser pulse of a petawatt laser pulses. And we see that at optimized plasma density, we can generate electrons more than 100 eV through the DRA acceleration. And the electrons more than 10 MeV has a charge of 50 nanocoulomb, which is 100 times more than the LWF electrons. And this figure shows how the electrons are accelerated inside the laser field. And this is the laser pulse leading the electrons. And this is a simulated electron spectra. And guided by the simulation result, we perform a collaboration experimental campaign in Guangzhou, IBS, just And this is our experimental team. A very nice feature of their facility is that they have a very double plasma system, which can ensure that our targets will not be damaged by the pre-pulses or AIC of this PETVA laser, which guarantee the very sharp plasma gradient as we expected. And in the experiment, we tried two kinds of targets. One is the single layer CNT target with a slightly higher density, and another is a double layer target composed of NCD carbon nanotube and a very thin diamond-like carbon force. In these two targets, in the first target, the major X-ray generation mechanism is a synchrotron emission, which happens when the electrons are accelerated and vigor in the self-generated magnetic field. And in the double layer target, in addition to the synchrotron emission, when the laser pulse is reflected by the solid fall, this nonlinear Compton scattering can boost the photon, further boost the photon energy and generate very high energies through the nonlinear Compton scattering mechanism. And this is what we designed method. And this is experimental setup. We use three kinds of different X-ray diagnostic method, including the filter stacks, Ross filters, and another kind of those filters in the backward direction. And all the electrons are bent away by the magnetic field. And this is a raw data from this Ross filter, which measures X-rays in the 8 to 100 keV. As we can see, this is from 3 continuous sources. The results are similar, which indicates that these results are highly reproducible. And this is the retrieved spectra. And in this filter stack diagnostics, we can measure the electron spectra from 100 keV to 1 MeV. And we utilizing this gentful simulations to simulate the response of this multiple image plates in this spectrometer, and retrieved these spectras. And as we can see, in the different schemes, the X-rays, the yield of the X-rays are different. In the doubler case, it's called the Compton scatter regime. The photon numbers is much significantly higher, and the energy is also higher than the single layer target case, which is consistent with our expectation. In the end, we combined these two different diagnostic methods into one single spectrum. As we can see, the two different methods, they meet with they fit with each other very well. And in the case of double layer target, we can obtain efficient, effective photon temperature of about 290 keV. And the highest photon energy measured by our diagnostic is around 1 MeV. And in the single layer target, of course, both of the photon numbers and the photon energies are reduced. These figures, we also performed a very detailed PIC simulations to explore the photon generation process. And in this single layer target regime, as we can see, the photons are generated when the electrons are propagated in this plasma channel. In this figure, this counter plot corresponds to the photons numbers, instant generated photon numbers. As we can see, they are gradually generated with the propagation of the laser and the generation of the electrons. And this is the end of the plasma. And when the laser propagate out of the plasma, the photon generation is stopped. In the Compton scatter regime, instead, as we can see, it also has some synchrotron photons, but the major high energy photons, they are generated in front of this second fall, when the reflected laser pulse is colliding with electrons, as we can see here. The photon energy is up to 1 MeV. We compared, it's interesting to compare our result to the LWFA X-ray sources. As we can see in these figures, our regime actually worked in the regime of very large laser amplitude. In our case, it's about 20. And also very high electron density, which is close to the critical density. And all other LWFA X-ray sources, they located in the left down corner. As we can see, their laser intensity is lower and the plasma density is also lower. As a result, the photon yield, which means the photon numbers per joule laser energy, which is indicated by the size of the ball, as we can see here, right? They are much smaller than what we obtained in this work. Eventually, we calculated that the photon yield is more than 10 to 10 photons per joule. These photons are hard X-ray photons, by the way. And so our sources is very beneficial for applications that need high photon numbers. Of course, we also measured that the divergence of our source is much larger than the LWFA X-ray sources. It's in a range of radius. This somehow is not good if we want some collimated X-ray sources. But on the other hand, if we want to a large field of view for X-ray imaging, it means that we can put the target, the objective, closer to the X-ray sources and give a very large field of view. And we can also make a comparison as to other light sources, including the undulators and wigglers. And these figures show that the red curves are the spectra we measured in our work. As we can see, they are comparable to the synchronous sources, third generation synchronous sources. And the critical photon energy is around 100 keV. More important, our simulation indicated that if we can further increase the power, the laser power to 10 petawatt, actually we can, by using the same targets, we can generate 10 MeV gamma rays with a very high brilliance. And this is a much, so this brilliance is much higher than the gamma ray sources by utilizing the conventional electron accelerators by around 7 or 8 order of magnitude, which is very promising for the gamma ray nuclear physics. And also because our work attracts a lot of interest in the field. Thanks to Professor Machi, they wrote news and reviews in the same issue of this Nature Photonics, and to give out a very nice review of our work. And they also highlight that it's possible that if we can use a 10 petawatt laser pulse, it's very exciting to generate gamma ray sources with much higher brilliant than the current conventional sources. Okay, in the end, I have to make some introduction to other work recently we made by using the CNT targets. And because we can tune the density and the thickness of the targets in the near critical density range, and so we can choose to interact in this underdense regime or slightly overdense regime. And in these two regimes, we have already demonstrated that the CNT target are very nice target for the enhanced ion acceleration. If you are interested, you can read these papers. Okay, now that's a summary. Carbon nanotube targets have already shown their advantage in the hard X-ray generation and the ion accelerations in recent years. And we achieved a very high photon yield of 10 to 10 per joule with an unprecedented efficiency of 10 to -3. And that's peak brilliance are comparable to synchrotron sources. And with upcoming 10 petawatt lasers, and such targets are very promising to deliver 1 to 10 MeV photons with brightness outperforming existing sources by 2 orders of magnitude. Okay, that's all of my presentation. Thank you.
Thank you, Professor Ma, for your impressive talk and also your contribution to the journal High Power Laser Science and Engineering. And we really appreciate your willingness to join this symposium in such busy schedule. Thank you. And I wonder if there's any question to Professor Ma's talk.
Hi, Wenjun.
Yeah, hi. Hey,
Yeah.
Professor.
So,
yeah.
So very exciting talk. And actually, we almost performed the very similar experiment by using the near critical density target. However, what we used is a unique designed gas nozzle. Well, I think your target is quite unique, and because you use this kind of nanotube target, so it's very easy to control the target configuration. I mean, quite followed by under critical target is an overcritical target. So you can very easily design this plasma structure. So congratulations. Yeah.
Thank you very much.
And, yes,
Yeah,
and I have a very small question. And you calculated your brightness is 10 to 21, right? Yes.
Oh. Yeah, 10 to 21, yes.
Maybe last page.
Last page. Wait. You mean this page, right?
No. The
brightness, peak brilliance.
Yes, 10 to and I also say the LWFA with the brightness is 10 to 21 to 23, right?
Yeah. Yes. Yeah, so, LW, yes, as we can see, yeah, here, yes.
Yes. So I think your photon number is much higher, right?
Yeah, because of a much higher, larger divergence angle.
Divergence angle. How is your source? I mean, source size.
Source size we didn't measure. We can only calculate from the simulation. It's around 10 micrometer something. Yeah.
10 micro. Yeah. So it's wow. Okay. So I think the large divergence angle is also good for some applications.
Yes, exactly.
For example, some large size sample. Suitable for this kind of large divergence. And also, we also experimentally observe this kind of large divergence angle Yes.
Yes. I heard that. Yes. So that's why we say we are in the same track to try to demonstrate and also try to apply these sources in nuclear physics or other fields, if possible. Yeah.
Yes. Good. Congratulations. Okay.
Yeah.
Okay, so thanks, Professor Chen, for your question, and also thanks, Professor Ma, for answering the question. So maybe let's now move to our last lecture, which will be led by Dr. Hui Zhang from Shanghai Institute of Optics and Fine Mechanics at Chinese Academy of Sciences. Dr. Zhang is member of the Youth Innovation Promotion Association of Chinese Academy of Sciences, and his main research field is the ultra-intense laser plasma interaction, especially laser-driven ion acceleration and also its application. So welcome, Dr. Zhang.
Okay, I'm sharing my screen. Okay, I'm ready. Can you hear me and see my screen?
Yeah, very well.
Yeah. Okay. I'm ready. Thanks for the introduction and invitation. Good morning, everyone. I am Zhang Hui, and I come from Shanghai Institute of Optics and Fine Mechanics. Today, I am very glad to share our work here, and I will give a presentation with the title of Surf Laser-Driven Proton Acceleration. SURF represents the Shanghai Super Intense Ultra-Fast Laser Facility. My presentation has 4 sections, including research background, introduction of surf laser and experimental platform, the recent progress of surf laser-driven proton acceleration, and a summary of a presentation. Firstly, I will give a brief introduction of research background of laser-driven ion acceleration. Chirped pulse amplification CPA technology has significantly advanced the development of ultra-short, ultra-intense lasers in the past few decades. The laser power is enhanced to a petal level, and the laser intensity goes beyond the relativistic threshold, about 10 to 18 watt per square centimeter, for the laser wavelengths of 1 micrometer, which provides the favorable conditions for the laser-driven particle acceleration. Compared to the traditional ion accelerators, the ion sources accelerated by intense lasers has unique characteristics, such as ultra-high acceleration gradient, ultra-short pulse duration, ultra-high flux. Laser-driven ion acceleration is attracting the widespread interest because of prospects of realizing compact and ultra-fast ion sources. Laser-driven ion sources can be used for many exciting applications, including inertial confinement fusion, proton radiography, simulation of space radiation environment, cancer therapy, and the generation of a neutrino antiproton. Many of these applications require high-energy ion beams with a narrow energy spread as well as a high flux. However, the quality of the ion beams obtained in experiment at present is still far away from the application requirement. Secondly, I will introduce the self-facility and the experimental platform. Self is the first 10 petawatt class laser facility in China, located in the Shanghai Pudong New District, which was proposed and constructed by the Shanghai Institute of Optics and Fine Mechanics in July 2016. The left photograph are the surf building and the laser facility hall, respectively. In 2017, the surf 10 petawatt beam line has realized the output peak power up to 10 to 3 petawatt with 339 joule output pulse energy compressed to the 21 femtosecond pulse duration. This peak power was further increased to the 12.9 petawatt in 2019. This figure shows the layout of the surf laser facility. The level lasers are located at the first floor of the surf building. The surf laser employs a typical CPS scheme and contains two high-intensity laser beam lines, surf 10 petawatt laser and surf 1 petawatt laser. Surf 10 petawatt laser operates at a repetition rate of 1 shot per 3 minutes, and the surf 1 petawatt laser operates at a repetition rate of 1 shot per 10 seconds. The physical experimental area of the surf building includes 3 research platforms: dynamics of materials under extreme conditions, DMEC platform, the big molecular dynamics and extreme fast chemistry, MODEC platform, and ultra-fast subatomic physics USAP platform. Our experimental study was performed on the USAP platform, located at the basement 2 floor. The surf 10 petawatt beam line is transmitted to the basement 2 floor through the transmission pipeline, further expanded and imaging relayed into the compressor cavity. Then the compressor laser pulse is optimized and focused on the target at the experimental area. This is a photograph of the experimental area in the USAP platform. Behind the compressor chamber are the beam quality improvement chamber and the experimental chamber. The beam quality improvement chamber is specially designed to place the deformable mirror and the plasma mirror to improve the beam quality and contrast. The experimental chamber for the laser metal interaction comprises 2 vacuum cavities. The larger one is for the shorter focal length experiments, like laser-driven ion acceleration, while the smaller one is for the longer focal length experiments, such as laser wake fields acceleration of electron. The main research fields of USAP platform includes the laser-driven ion electron acceleration, laser-driven radiation source, laser-driven antimatter production, high energy density physics, laser nuclear physics, laboratory astrophysics, and so on. The USAP experimental platform has 4 systems: vacuum system, optical system, diagnostic system, target system. The vacuum system has a larger chamber with a size of 5.2 meter times 4.2 meter times 3.5 meter, and can provide the ultimate vacuum of 8.6 times 10 to minus 5 Pa. The function of optical systems is to further improve the beam quality and the contrast, and focus the laser using off-axis problem mirror with the different f numbers. The diagnostic system has a specially designed detectors to measure the ion, electron, and gamma sources driven by the lasers. Besides, we have installed a high precision 3-dimension printers and can provide targets with different structures based on the experimental demand. Next, I will present the recent progress of the surf laser-driven proton acceleration. The experimental results from the surf 1 petawatt laser beamline are first introduced. The experiment on the surf 1 petawatt laser was carried out in 2019. The target is 10 micrometers aluminum foil. There was a strong pre-pulse at 3 nanoseconds prior to the main pulse, which resulted in many interesting phenomena. From the proton profile measured by the radiochromic film RCF stacks, we can see that the low energy protons show the ring-like profile, and the high energy protons show filamentation structures. To better understand the experimental results, we first performed hydrodynamic simulations to study the effect of pre-pulse on the density distribution of target. It shows that under the pre-pulse irradiation, a larger scale pre-plasma appears on the front and the rear of the target. Based on the pre-plasma distribution, we further carried out the particle-in-cell PIC simulations to study the main laser pulse interacting with the pre-expanding target. The PIC simulated results indicate that magnetic fields with different strengths and lifetimes developed on the rear of the target. The short-term filamented magnetic field via the Weber instability results in the filamented proton profile at the high energy range. The long-term quasi-static annular magnetic field induced by the streaming electron current results in the ring-like proton profile at the low energy region. This kind of proton beams affected by the magnetic field tends to be non-laminar. We use the knife edge method to measure the size of the non-laminar proton sources. The upper row shows the experimental setup. Knife is a metal foil with 200 micrometer thickness and 3.8 millimeter width, located behind the rear of the target. The proton profile is recorded by the RCF stacks. From the proton profile, we can see the distinct knife edge. The optical density distribution around the knife edge shows that there are 3 regions: exposure region, penumbral region, and the shaded region. Based on the width of the penumbral region, the size of a proton source can be calculated according to the geometric relation. In addition, we also use the mesh imaging method to measure the proton size. This is the experimental setup. The copper mesh is located behind the rear of the target, and the RCF stacks are used to record the distribution of protons passing through the copper mesh. The experimental results indicate that the proton size with the mesh imaging method agree well with those of the knife edge method. We analyzed the proton source size as a function of the proton energy. We find that the size of the proton source decreases linearly with the increase of the proton energy. The minimum size is about 30 micrometers for the 14 MeV protons. Next, I will present the experimental results from the surf-time petawatt laser beamline. There are 3 experimental campaigns on the surf-time petawatt beamline. In the 2020, we conducted the first experiment during the USIP platform acceptance. The laser power on target is 2 petawatt, and the focal spot is 6 micrometers in diameter, resulting in an intensity of 1.7 times 10 to 21 watt per square centimeter. However, the laser contrast is poor, with obvious repulse on the picosecond and nanosecond scale, reaching 3.7 times 10 to minus 7 at 8.6 nanoseconds prior the main pulse. The target used in experiments are the copper foils with a thickness varying from 4 micrometer to 30 micrometer. The experimental results shows that the optimal target thickness for the proton acceleration is 15 micrometer. Finally, with a 15 micrometer thick foil, we achieved 27 MeV proton beams with a divergence angle of 4 degree, proton size of 9 micrometer times 30 micrometer, and the proton numbers of 4.7 times 10 to 10 for the energy more than 10 MeV. The second experiment was carried out in 2021. The laser power on target is 2.4 petawatt, and the intensity is 2 times 10 to 21 watt per square centimeter. It should be noted that the laser contrast was optimized and some repulses are removed. The target used in experiments are the copper foil with the thickness varying from the 1 micrometer to 10 micrometers. Here, 2 Thomson parabola spectrometers at the laser and the normal directions are used to detect the proton energy spectrum. The specially designed stacks of the RCFs and the imaging plates eyepieces are used to measure the profile of and energy spectrum of the protons and the electrons at the selected energies. These are the main experimental results. The optimal target thickness for the proton acceleration is 4 micrometers. For the 4 micrometer thick foils, the average cutoff energy of protons is 16 MeV, according to the data from the 3 shots, where the highest one achieves 16.5 MeV. Compared with the results of the 2020, the optimal target thickness reduced from the 15 micrometer to the 4 micrometers, and the proton cutoff energy increases from the 27 MeV to the 16 MeV. The proton energy along the target normal directions are much higher than those along the laser direction for the all target thickness. Typical proton spectra for the various target thicknesses shows the broad energy spread distribution. We also analyzed the distribution of protons and electrons obtained from the RCF and IP stacks at different energies. From a typical proton distribution, it can be seen that the proton signals and the divergent angle decrease at higher proton energies. The electron spectrum can be calculated from electron distributions of different energies. The fading curve of the electron spectrum indicates an electron temperature of 7.6 MeV, which agrees reasonably with the theoretical results of 8.6 MeV, following the Pandora-motive scaling law. The features mentioned above, including the proton spectral, proton distribution, electron temperature, suggest that target normal phase acceleration (TNSS) regime is dominant in the self-accelerated 16 MeV proton beams. The third experimental was carried out in 2021. The laser contrast was further improved with a single plasma mirror installed out of excess problem mirror, which allows the self-time pedowa laser interacting with a nanosecond thick hydrocarbon foil. The laser power on target is 1.7 pedowa, and the intensity is 1.4 times 10 to 21 watts per square centimeter. Using the lower energy laser interacting with the nanometer thick firmware foil, the 17.2 MeV proton beams was obtained via the relativistic induced transparency regime. This work is a preparation. The target used experiment mentioned above is a micrometer or nanometer thick flat foil. Next, I will present the experimental results of high efficiency proton sources using the microstructure. There are two experimental campaigns using the microstructure to accelerate the proton. The first experiment was carried out on Jardine pedowa laser system in 2020. This is the experiment setup. The laser power on target is 0.4 pedowa, and the laser intensity is 2.2 times 10 to 20 watts per square centimeter. We used the high precision, the three-dimension printers to manufacture the microwire array target. The microwire targets comprise the microstructures and 1 micrometer SIN substrate. The microwire structures have the same height and diameter, but the structure period varies from 1.3 micrometers to 3.3 micrometers. We observed the enhanced proton acceleration with this microwire array target. The left figure shows the main experimental results. The upper row of the figure shows the proton cutoff energy and the proton and the laser proton energy conversion efficiency as a function of the target thickness and the microwire period. The lower row shows the proton energy spectrum. The black points represent results from the flat target. We can find that the optimal target thickness is around 1 micrometer. Red point represents results from the microwire target. It can be seen that the proton energy increases with the increase of a wire period. At a wire period of the 3.3 micrometer, the proton energy reaches a maximum of 25 MeV, enhanced by the 13% compared with the flat foil. Especially, the conversion efficiency from the laser to a proton comes up to 8.7%. To perform the hydrodynamic and the PIC simulations to estimate the pre-plasma distribution of microwire structures induced by the pre-pulse. Hydrodynamic simulations show that under the pre-pulse irradiation, the top of the wire expands more than the root. The PIC simulations suggest that the laser diffractions can result in the different pre-expansion plasma at different locations. The laser field is diffracted by the periodic structure such that it is located intensified around the tops of the pillars. Modulated laser intensity produces the pre-plasma of a larger scale length. Based on simulation results, we set the density distribution of a pre-expanding microwire array targets. Each pillar is surrounded with the modulated pre-plasma of the two components. Around the top, the pre-plasma forms a semicular density profile. The pre-plasma density in the rest area is exponential decay, with the scale length decreases decreases with the increase of the distance from the top of the wire. The other PIC simulation was carried out to study the laser pulse interacting with the pre-expanding microwire target. The simulated results shows that compared with the case of the flat target, the electron energy is higher and the sheath field is stronger for the case of microwire target. Accordingly, the electron enhancement results in the enhanced proton acceleration, which agrees with the experimental result. In the case of the microwire target, considering the pre-plasma, the energy and the sheath fields reduce. The right figure shows the proton energy varying with the period of the microwire structures. There is an optimal structural period for the proton acceleration. Considering the pre-plasma, the optimal structure period will increase and the proton energy will decrease. The second experiment using the microwire targets was carried out in 2021 on the served 10 petawatt beamline. A single plasma mirror was used. The laser power on target is 1.7 petawatt, and the intensity is 1.4 times 10 to the 21 watt per square centimeter. At a high laser contrast, we also observed the enhanced proton acceleration. The proton beams with the energy of 62.8 MeV was obtained at an optimal period of 2 micrometer, which is enhanced by the 36% compared with the flat foil. This work is also in preparation. At last, I will give a summary of the presentation. Based on the surf laser facility, we built the 10 petawatt laser plus the experimental platform USIP. Using the 2.4 petawatt laser interacting with the micrometer thick copper foil, the 16.5 MeV proton beams was obtained via the target normal phase acceleration regime. After the optimizing the laser contrast with the plasma mirror, using the 1.7 petawatt laser interacting with the nanometer thick hydrocarbon foil, the 17.2 MeV proton beams was obtained via the relativistic induced transparency regime. Using the 1.7 petawatt laser interacting with the microwire target, the 16.2.8 MeV proton beams was obtained at the optimal period, which is enhanced by the 36% compared with the flat foil. In the future, we will further optimize the laser focal spot and the laser contrast and enhance the laser power. The proton energy may be increased to 100 MeV using the optimized laser interacting with the nanometer thick foil or the microstructure target. That's all my presentation. Thanks for your attention, and congratulations on the 10th anniversary of the high power laser science and engineering.
Thank you, Dr. Zhang, for your presentation, and we definitely look forward to see more progress of you and your team's research. I wonder if there's any question for Dr. Zhang's presentation from our audience in live stream platform or from our panelists.
Hi, Dr. Zhang. Yeah, a very fantastic talk. And actually, your laser, I saw it's optimized step by step, and right now you can got 1.7 petawatt with a very high contrast. I mean, you use a plasma mirror, right?
Yes,
so,
yes.
Yeah. So I started wondering, you accelerated the ion energy, I mean the proton energy higher and higher. Right now it's I saw it's over 7 MeV. So that's fantastic. So in your experiment, did you see any, I mean, the energy spread of this proton acceleration is very critical for some applications, for example, the cancer therapy. So did you observe any phenomenon for this small energy spread? I mean, the more energetic structure of your proton beam.
You mean in experiment we observe the narrow energy spread of the protons? Yes.
Because that's
in some shots we observed the energy the narrow energy spread we actually observed the energy spread, but it's not protons. It's a carbons.
Carbon.
Yeah, carbon.
Okay.
Protons it's usually
carbon ion is also very good.
Yeah.
So how about the energy spread?
It's several percent.
Several percent. Oh.
Yeah, several percent. Several to 10.
Wow,
10%.
fantastic.
Ever to 10. Yeah.
So you think the acceleration mechanism is RPA or something else?
I think RPA play an important role, but the laser is linearly we used, so the TSA is also. So I think the acceleration regime is it's RPA and the TSA hybrid the regime.
Oh, okay, hybrid, yes.
Hybrid.
Because actually your laser intensity is high enough to drive the RPA. I mean, really got some more energetic ion beam. That's very important for this field. Okay.
Yeah.
Congratulations.
Oh, thank you, Professor Chen.
Okay, thank you, Professor Chen, for your question and comments to Dr. Zhang's presentation. Are there any other questions from our other guests today?
Yeah, I have a question. Yeah. Dr. Zhang, yeah, very nice work. Very long time effort pursuing high energy protons. And I see that you have already implemented this plasma mirror system, right?
Yeah.
It's a recollimated plasma, or it's a target front plasma mirror. Is it a recollimated plasma mirror, or it's a position in front of the target? What kind of plasma mirror?
The plasma mirror is installed after the off-axis problem mirror.
Oh, okay.
Yeah.
So it's a target front plasma mirror, right?
Yeah.
Okay, well, it's a double plasma mirror or single plasma mirror?
A single plasma mirror.
Okay. Do you have a plan to implement a double plasma mirror to further increase the contrast?
Because maybe in the future we will use two plasma mirror. It's also installed after the OIP mirror.
Okay, I see. Yeah, looking forward to a new result. Very nice.
Yeah. Thank you.
Okay, thank you, Professor Ma, for your comments to Dr. Zhang's presentation. If no further question for the presentation, we thank all our speakers and audience today. And we will be sending the recording of this event to our registrant after this symposium. So those who were not able to join lively today will be able to watch the recording afterwards. And we do hope that all the lectures today we have would be interesting for you. And we look forward to seeing you again in our future activities. So have a nice day and have a nice evening. Thank you.